Let's do a quick video on homework 2C where we're supposed to put together a lot of concepts that we've been covering plus a review of EE98. And here we have a low pass filter or an RC circuit. We have that's put into an ideal op amp with a gain stage, and that's put into another ideal op amp with a gain stage. To orient ourselves, I've given a positive plus 5 volts for the power supply and a minus 5 volts for the negative power supply. What we have here is to try to make it more generic, I've tried to do some programming. And so I have a parameter called R5, which is 10K. And you just put those curly brackets in there, and whatever you change it, it'll change it there. 10 nanofarads for C1. And how long should the pulse take to rise up, or what's the maximum? And a good estimate for that is take whatever tau is, right, and just divide it by 100. So in this case, tau would be R5 times C1 because it's a first order idealized circuit. So we just rise time, take tau divided by 100, fall time, make it symmetric. We're going to program what voltage it turns on to. So it'll start at 0, go on to 1 volt. How long should this pulse width stay on? 5 tau. That should give you the full kind of range. And the period, we should just make 2 times t on. St is my variable for simulation time. So down here, transient, simulate for that amount of time. And then the gain, I just programmed it. So I look at this, it's an ideal op amp. The gain is 1 plus R2 divided by R1, and I just made the gain stages equal. So yeah, I mean the K's cancel out, so I just programmed it 1 plus 30 divided by 10. So that's 4 times 4. All right, so I should get a total gain from here to here of 16. So let's run it. And my Spice sometimes does something. So we'll just look at our V out. And there's an issue here, right? It kind of looks like I have a linear thing, then it's just complete, then it's flat, and then it looks like exponential decay. All right, maybe I did the input incorrectly. So let me plot V in. But no, it goes 0 to 1, and it goes on for 5 tau, which is in our case 500 microseconds. So that's set up right. What could it be? Well, maybe I did something incorrectly here. So I'll click on node 1, and that should just be a step function of a low pass filter, and I see that it rises up and it takes 5 tau to get there, and it goes discharges in another 5 tau. So the low pass filter is working properly. All right, it goes through a gain stage of 4. What about that? And we see that it rises up to 4 because 1 times 4 is 4 and discharges back to 0. That's not a problem. But then it seems to be clipping at 5 volts. Probably most of you have seen where this is headed and have figured out that when I multiply 1 volt times 16, I need to go to 16. So either my power supplies need to go to plus or minus 16, or I need to check my V on to something that won't saturate the gain. So really I can just, rather than divide it by 16, I'll just divide it by 20 or 50 millivolts. So we'll rerun it. All right. And now we see that now we're not going up to 1 volt for the input, but we can see that it scales. This is 4 times that, and this is 16 times that, and now it's working. Now sometimes you don't know, you want to compare it against some kind of idealized thing. So I've actually programmed a step function here. I mean, I programmed a behavioral source. I've called it step, right? And it's just 1 minus the exponential decay times the step function. I subtract it, and over here I'm multiplying it times the gain. So I'll just click on step, and I'm just going to delete the other waveforms. Now it matches pretty well. This little error here will be due to the fact that the rise and fall time aren't 0, right? But that's not a real thing. So it's matching there. Now you're supposed to also derive the step response, impulse response and the ramp. Well, to find the impulse response, you just take the derivative with respect to time of the step, which can be done in LTspice like this. And for the ramp, you're supposed to take the integral. Now for the homework, you're supposed to do this mathematically. I'm just showing you the concept of how you're supposed to link these things. So let's click on H, and when we take the derivative of the step function, yeah, it goes up to 8 kilovolts and goes down to minus kilovolts, which it is the step response, it's the impulse response, even though our function generator, I couldn't create an 8 kilovolt input to make that happen. Let's look at the ramp. We have to delete H, otherwise it won't scale correctly. And get rid of the steps. And we can see that as it's integrating up, it integrates up and then levels out. And we can see that if what I'll do is add another plot plane. Now, my bad. Right? And so we can see that it's integrating. The area is getting bigger and bigger and bigger. And now we're still integrating. The area is getting bigger, but it's just not getting big as fast till at some point it almost hits 0, and so the integration stops. Okay. And so really, if you have one, you should be able to derive the others. We have some review here of that. If you have a non-inverting amplifier, right, the gain is 1 plus the feedback resistor divided by the resistor tied to ground. We cascade gains together, and then whatever here we have at the input just gets multiplied by those gain stages. And yeah, here's a way to check your work in LTspice. And that should help you with your homework.